When a steel I-beam is placed under extreme load, it yields, buckling and tearing apart. This failure is what we observe on a macroscopic scale, but the timing and location of that tear are dictated by the movement of atomic defects. Macroscopic collapse is the aggregate result of microscopic shifts within the metal's crystal structure. Dislocation theory allows us to study these moving line defects within a crystal lattice. The challenge lies in calculation. When a complex three-dimensional stress is applied to the bulk material, we need a way to determine the exact directional force acting on a single microscopic dislocation line. This is the Koehler equation. It provides the framework to compute the force per unit length acting on a dislocation by utilizing a stress vector, g, to process the local stress components. By deriving this equation, we can mathematically demonstrate why different types of dislocations react in specific ways to the same external forces. This derivation serves as the key to translating macroscopic stress tensors into predictable microstructural defect motion. We begin by establishing a three-dimensional Cartesian coordinate system using x, y, and z axes. Within this space, we define an arbitrary dislocation line direction, xi, and its associated Burger's vector, b. In this mixed dislocation model, the two vectors are neither parallel nor perpendicular. We also define the 3x3 macroscopic stress tensor, sigma, which represents the external forces applied to the material. Step 1 of the derivation requires the dot product of the stress tensor and the Burger's vector. This operation generates the intermediate stress vector, g. This g vector represents the local stress components acting specifically in relation to the magnitude and direction of the Burger's vector. Step 2 is the cross product of the stress vector, g, and the line direction, xi. This calculation determines the final force vector, Fl. This cross product ensures the resulting force acts exclusively perpendicular to the dislocation line, which dictates the geometric rules for how the defect moves. We can apply this general equation to a specific case, the purely screw dislocation. In a screw dislocation, the defining boundary condition is that the Burger's vector and the line direction are parallel, both aligned here along the z-axis. This specific geometry generates a unique elastic stress field in the surrounding crystal lattice. The equations for this stress field show that the normal stress components, sigma xx, yy, and zz, are all zero. This means the stresses acting around a screw dislocation consist solely of the shear components, tau xz and tau yz. The parallel geometry effectively removes normal stress from the calculation, creating a purely shear-driven environment for our derivation. Performing the internal dot product for a screw dislocation involves multiplying the stress tensor by a Burger's vector of 0, 0, 1. Multiplying by this unit vector extracts only the third column of the stress tensor, simplifying the intermediate stress vector to these three shear and normal components. Next, we set up the determinant matrix to calculate the cross product of that result with the line direction, c. The resulting vector equation shows that the force has no z component. Because the force is restricted to the xy plane, it acts entirely perpendicular to the dislocation line, regardless of the line's length. This proves that screw dislocations are driven only by shear stresses, which results in the mobility mechanism known as cross-slip. Now we transition to the straight edge dislocation. For an edge dislocation, the boundary condition changes. The Burger's vector and the line direction are now strictly orthogonal. This shift to an orthogonal geometry results in a more complex elastic stress field. Unlike the screw model, the edge dislocation stress field contains both shear stresses and normal stresses, creating distinct regions of compression and tension. The shear stresses related to the z-axis are zero, leaving only the in-plane shear components and the normal stresses. This combination of normal and shear forces changes the mathematical output we will get from the Koehler equation. In step 1 for the edge dislocation, the dot product uses a Burger's vector of 1, 0, 0. This operation extracts the first column of the stress tensor, which includes the normal stress in the x direction. We then calculate the final cross product to determine the force vector direction. The result is a force with two distinct components. These two components represent two different physical responses of the dislocation line. The first component is the Fx force, a tangential force driven by shear that causes the dislocation to glide along its slip plane. The second is the Fy force, a normal force driven by normal stress. This is the climb force. This climb force causes the dislocation to move vertically, a process that requires the absorption or emission of atomic vacancies in the lattice. The derivation proves that because of normal stresses, edge dislocations have access to climb, a mobility mechanism that is mathematically zero for screw dislocations. These derivations establish the mechanical differences between these two types of defects. While pure shear drives screw dislocations, edge dislocations are moved by both normal and shear forces. This leads to the different mobility mechanisms we've explored: cross-slip for screw dislocations and glide and climb for edge dislocations. This explains how a material under a uniform global stress state can experience varying local forces at the microscale. The specific force depends entirely on the orientation of the dislocation line and its Berger's vector relative to the stress tensor. Applying this framework is essential for predicting the mechanical behavior of metals. By calculating these directional forces, engineers can model behaviors like work hardening and high-temperature creep. The Koehler equation serves as the foundation for physically predicting and controlling the mechanical behavior of modern materials. These derivations establish the mechanical differences between these two types of defects. While pure shear drives screw dislocations, edge dislocations are moved by both normal and shear forces. This leads to the different mobility mechanisms we've explored: cross-slip for screw dislocations and glide and climb for edge dislocations. This explains how a material under a uniform global stress state can experience varying local forces at the microscale. The specific force depends entirely on the orientation of the dislocation line and its Berger's vector relative to the stress tensor. Applying this framework is essential for predicting the mechanical behavior of metals. By calculating these directional forces, engineers can model behaviors like work hardening and high-temperature creep. The Koehler equation serves as the foundation for physically predicting and controlling the mechanical behavior of modern materials.